All right, so let's fill in these 2.6 guided notes. So this is going to be all about transformations of functions, which is how functions move when you change their equations. And it should be connected to the activity that you did on Desmos, where you were playing around with the graphs and seeing what happened when you move sliders. So the first part of this is going to be filling out a bunch of terminology. So the simplest function in a family of functions is called the parent function. And the graph is called the parent graph. Whenever you make a change to a parent equation, it results in a change in the parent graph. It moves the graph around somehow. That change is called a transformation. Now, in the Desmos activity that you played with last time, you should have noticed that you had several different types of transformations. One of them was when the graph would just move left or right or up or down without actually changing size or shape. That transformation is called a translation. So it's sliding a figure from one position to another without turning it or changing its shape. Now, you may have also seen graphs that flipped over an x-axis or flipped over a y-axis. A flip is called a reflection. And the line that you flip it over, which is the x or the y-axis depending, is called the line of reflection. You may have also seen some shapes that were stretched or compressed up or down, or stretched or compressed side to side. Whenever you're stretching or compressing something, we call that a dilation. Kind of like you dilate your eyes with the eye doctor. Now, the goal of what we're going to be doing here is sort of taking the parent functions, the simplest ones, and then using transformations to draw graphs once they've been transformed. So the first thing we need is to get the parent functions for a few functions that we're working with. We're going to start with three of them. Y equals absolute value of x, y equals x squared, y equals x cubed. There are a grand total of 12, I think, in math, but we're only going to work on these three for now. We're going to slowly add more parent functions as we move through the course of the year, but these transformation rules will always be the same. So to build the parent functions, what we're going to do is we're going to make little baby t-charts, and these baby t-charts are all going to have the same x values in them. So -2, -1, 0, 1, and 2. Now, I basically fill in the t-chart by plugging each of the x's into the parent function. So the absolute value of 2 is 2, absolute value of -1 is 1, of 0 is 0, 1 is 1, 2 is 2. When I plug it into x squared, -2 squared is 4, -1 squared is 1, 0 squared is 0, and so forth. When I plug it into x cubed, -2 cubed is -8, -1, 0, 1, and 8. So these are the points that are going to be on my parent functions. So I'm going to draw in some axes. Ooh, that's not a really good axis, but we'll work with it. Plot the points that I have on my t-chart. And then connect those points to form the shape. So that's the parent graph of absolute value of x. So I'd like you to pause the video and to go ahead and plot x squared and x cubed, and when you unpause the video, those graphs will be drawn. So here are the other two parent graphs. Now, you will need to either memorize the shapes of these graphs. I think it's best to remember how to build the t-charts for each of the parent graphs, so you can simply recreate the parent graph when you need to. All right, let's move to the second page. Now, the rules for transformation, there are 8 of them, and this is a typo, this should be a minus. There are 8 rules, but they all boil down to 2 rules, which I'll basically tell you in just a moment. So when you add a number outside the function, that's like adding a number to the y value, because f of x is the same thing as y. That is going to translate the graph up b units. So if I subtract b, that's going to translate down b units. Now, when you do it with the x, if you played with the Desmos activity at all, you notice that the slider moved, like when you moved it to the right, the graph moved to the left, and when you moved it to the left, the graph moved to the right. That's going to be pretty much always true for x stuff. It's always going to do the opposite of what you think it will be. So adding b to an x actually moves the graph, translates it to the left b units. And we're going to talk about how that looks numerically in just a minute. Subtracting b then translates to the right. Multiplying -1 by f of x is like multiplying the y values by -1, which takes the ones that are up like above the x-axis and drops them below. And so what that basically does is it reflects over the x-axis. And if you play it again with the Desmos activity, then you would see that that's the case. Multiplying by -1 on the x reflects over the y-axis. Now, multiplying by b on the outside is like multiplying all the y values by a number. So that's going to take all the y values and sort of like stretch them if the number is bigger than 1, or shrink them if the number is between 0 and 1. So when you multiply by a b, that's a dilation. And it dilates the y's, so it dilates up and down vertically, by a factor of b. And we're going to talk about what that looks like in the next screen. Multiplying by b on the x also dilates, but it changes the x's, so it dilates horizontally. And it does the opposite of what you think it would. So instead of by a factor of b, it's a factor of 1 over b. And we'll talk about that in just a moment. Now, these 8 rules, they're always going to be consistent no matter what kind of function parent function you start with. But I like to think of these as being sort of like 2 rules. If a number is grouped with the x, it affects the x in the opposite way. And if it's not with the x, it affects the y in the same way. Now we're going to illustrate that in the next 3 examples on the next page, but these are the ways that I memorize the transformation rules rather than memorizing all 8 of these, but your mileage may vary. All right, so when I'm doing problems and I'm actually like executing transformation problems, I want to see 3 steps, and I'm going to do these 3 steps in those examples on the next page. So I'd like to see first to graph the parent, and then second, do any dilations and reflections. And then draw the final graph, which has dilations and reflections and the translations. All right, so let's do some examples so you can see how this operates. So the first thing I need to do is figure out what the parent graph is. So we have 3 parents right now, x squared, absolute value of x, and x cubed. And if you look at this, this is clearly an absolute value graph because there's absolute values in it. So the parent graph here would be absolute value of x. You look at the second one, parent graph, clearly x squared because there's a square in it. Bottom graph, clearly x cubed. So basically whatever operation you're doing to the x stuff, that's the parent graph in each of these situations. So I'm going to draw the parent graph in this first example first. So again, I would have that little t-chart. The parent graph for absolute value of x, -2, -1, 0, 1, 2. This is 2, 1, 0, 1, 2. When I plot those numbers, I get something that looks like that, which is the parent graph. Now, the dilation reflection step. So I look at the numbers that are different from the parent graph in the equation we're graphing. So there's a 2 here, there's the 3 here, and there's this -4 here. So you can see that the 3 is grouped inside the absolute value bars with the x. So that's going to affect the x values. And anything that affects the x values in the opposite way than you think it will. That was the rule that we wrote on the last page. The stuff that's not with x affects the y. Now, The dilation and reflection steps are basically multiplying by a number. So it's dilations are multiplying by a number whose magnitude, whose size is different than 1. Reflections happen when you multiply by a negative number. So we're multiplying by a 2 here. So this is going to be a dilation. But I'm going to execute that by actually thinking of the rules I said a second ago. When it's with the y, which this is, it's going to affect the y values in the same way it looks like. So we are multiplying by 2. So that 2 on the outside is going to multiply the y values in this parent t-chart by 2. The x values will stay the same because nothing's being multiplied by x, but the y values will be multiplied by 2. So I would plot those and if you look at that graph, you can see that it looks like it got grabbed by the bottom and the top and basically stretched. It's a vertical dilation. Now, that's the dilation step. So now we're ready to draw the final graph, meaning we need to work in these additions and subtractions. So we're adding 3 on the inside to the x's, but remember if it's with the x, it does the opposite of what you think it should. So we're really going to be subtracting 3 from all the x values in this t-chart. And then this 4 on the outside, by the way, that subtracting 3 would move the graph to the left 3 because you're subtracting 3 from all the x's. That negative 4 on the outside, that's with the y, it's not with x. So that's going to do exactly what you think it's supposed to the y's. So that's going to subtract 4 from all the y values, which will basically move the graph down. So when I do this to the t-chart, I'm going to subtract 3 from all the x's. And I'm going to subtract 4 from all the y's. And those are going to be the points on my final graph. So let's see, negative 5, 0, negative 4, negative 2, negative 3, negative 4, and so forth. So now if you look at the blue graph and the red graph, you can see it looks like the blue graph has been moved to the left 3 units and then down 4 units to land on that spot. All right, so let's do the second example. So again, we're going to start by drawing the parent graph. So the parent graph this time is y equals x squared. I'm squaring these to get the y values. Okay, there's the parent graph. So now I'm going to look at the numbers that are different from the parent graph, which are this and this and this. I'm going to classify them as being with x or with y, so that one that's inside parentheses is with x. These are with y, because they're outside the parenthesis. And then I'm going to do the multiplication thing first. So the multiplication thing, dilation reflection, is this negative here. It's not with the x, it's with the y. So I'm going to multiply negative 1 times y. I'm going to plot those points. And you can see basically that took the graph, when I connect those points, that it took the graph and it reflected it across the x-axis. So now I'm going to do the final graph. This negative 2 is with the x, so it's going to affect the x, but in the opposite way you think it will. So it's going to add 2. This positive 1 is with the y, so it's going to affect the y in exactly the same way you think it will. So it'll add 1. So I add 2 to all the x's. I add 1 to all the y's. And I plot those points. So 0, negative 3, 1, 0, 2, 1, 3, 0, and there. and that would be my final graph. Now, this last example. Parent graph is x cubed, so we're going to start by graphing that. Oops. With my little t-chart. Plot the points. Connect it to make my parent graph. Like that. All right, so I look at the numbers that are happening here. So I've got this 1/2 and this -3. Now, I want you to notice there are no parentheses or grouping symbols here. No parentheses or absolute value bars here. So there is nothing with the x. All the things that are here, the 1/2 happens after the x has been cubed, so nothing is with the x. Both of these are with y, which means they're going to affect the y values in exactly the way you think they should. So we do the multiplication step first. 1/2 times all the y values. And plot those values. Connect the points. Like that. And then I'm going to do my last graph. The -3 is with the y, so it affects the y in exactly the way you think it should. It's going to take 3 away from all the y's. The x's are still the same. Take 3 away from all the y's. Plot those points. And then connect those. And that would be what your final graph looks like. So essentially, it's drawing the parent graph, determining what transformations are happening to the x and to the y, doing the multiplication of steps first, and then doing the addition and subtraction.